Hello, everyone. I'm very happy to be here to present our work about ObliVM, that is a programming framework for secure computation. And this is a joint work with our teammates, Xiao Wang, Kartik, sitting there, and Yan Huang and Lan Shi. And so I'm very happy that my previous talk have extensively explained what is secure computation, aka secure function evaluation. I just give you a brief motivation that, for example, Sheldon and Amy here wants to find a good partner for each other, and then they all believe in genomic dating, and then so they can run their run analysis to see whether they are matched or not. So the key security question is they don't want to leak their sensitive genomic data to each other. So and we have been talking that secure computation is a good solution to solve this problem. For example, we can abstract this problem as following: given two parties, Alice and Bob, having their secret input X and Y. So they want to jointly compute a public function f over X and Y, get some results, and then the computation over these two secret inputs should not leak anything other than the result Z to each other. So this is secure computation, and we've been, so you already know there are Yale-Scarborough circuit and there are GMW protocols that can solve the secure computation. So what is our focus? Our focus is that how we can make secure computation really practical. For example, when developer want to develop secure computation applications, so they don't want to write in a circuit format. They want to write in a C language, write in a Java or Python language. So there is a gap between the source program and the actual secure computation protocol. So this is what our ObliVM framework do. So our ObliVM protocol, our ObliVM is a tool to translate source programs into the actual secure computation protocols. So okay, this is an overview, and then what is the main question? As Kartik just introduced, the question is that is the gap between the programmer's favorite model. For example, this is a Python-like language, and this is what the programmers really want to write. But actually, the most secure computation protocols are treating with this circuit model. So there is a big gap between the high-level language programs and the circuit. So our question is, how can we translate the left part into the right part? Okay, so and thank you very much, Kartik. You have motivated this well. So the key challenge here is that how we can make the dynamic memory accesses not leak information. So this is not a trivial challenge, but this is not a trivial task. So. But actually, our solution is that we want to translate the program in a RAM model language into its oblivious counterpart. So here, obliviousness means that memory accesses and the instruction traces do not depend on secret input. So that in this way, the oblivious program can easily transfer into a circuit. So we can see in this transformation, the later part is relatively easy, and the first part is really challenging. So this talk will focus on the first part and how to do that. So a very trivial, not trivial, but a solution that was proposed first in 2013 was to use oblivious RAM. So for oblivious RAM or ORAM, that can compile an arbitrary program into its oblivious counterpart. And based on this idea, last year we present our SCVM framework that does this work to simulate the generic ORAM. And we can show we can achieve asymptotic performance gain over all previous solution. However, this solution is generic and easy to implement, but the problem is that it might not be the most efficient way. So over the past few years, we have observed many customized secure computation protocols. There is a long list of all this work, and unfortunately, I don't have space to list them all. So they are very, very efficient, but basically, I can say they are more efficient than our last year's work. But the problem is that they incur very high design effort. For example, we have talked to Nina Tuff, that she is our collaborator, and we had a private conversation about their paper on private matrix factorization published in CCS 2013. And she mentioned to us that it spent a team of 5 researchers about 4 months to implement everything. So that is basically more than 1.5 research a year. So that was a big effort. So our question is that, can we make it better? So can we build a generic framework, but also achieve the customized performance? So this is about our work at ObliVM to achieve this goal. So we want to allow non-specialists, so for example, non-cryptographer, to implement some secure computation protocols while achieving the customized performance. So how do we do that? So the key idea is that within ObliVM, we provide several programming abstractions. For example, I list many here: oblivious data structures, MapReduce, and loop coalescing. But I will introduce one of them later, but for more details, I will refer you to the paper. And I also would like to mention that the GraphIC paper that was just presented by Kartik is also a program abstraction dedicated for parallel computing. So we provide program abstractions. So I will give you intuition about what it is. So let's think about the distributed community. I think most of you should heard of this, the MapReduce. That was published by Google in 2004 in OSDI. And before that paper was published, parallel computing or distributed computing was considered a hard task. But using MapReduce, the developer only need to only need to encode their computation into a mapper along with a reducer, so that developer don't need to worry anything about the distribution, but the MapReduce framework can do everything for you. So the development effort using MapReduce is very low comparing to previous work. So we take we want to take a very similar approach here. So we want to provide some abstractions to allow programmers to design their tasks, to encode their tasks into these abstractions, and so that they don't need to worry about the the underlying cryptography primitives, while achieving the same performance. So here is our goal. So here is our solution. So how can we provide these program abstractions? So we want to we want to implement a language support. So for example, we want to implement a new language for all developers. So when developing this language, we have 2 goals in our mind. The first one is that using our language, the expert or cryptographers can implement different programming abstractions very easily. And on the other hand, for those non-specialists, so for example, they do not know very much about the cryptography, then they can use these abstractions very easily to build their own applications. So with this goal with these 2 goals in our mind, then our solution is to support new language features that was never supported before by any previous system. And so I list a couple of them here, and I will refer you to the reader for more details. I can and further, we will open source our compiler here. So that you can know even more details about the compiler. So I think these features are really cool. For example, we can use those random type and phantom functions to actually implement the oblivious RAM protocols in the source level rather than as a backend primitive. And okay, so having all of this, then what programmer can do? For example, we want to implement a sparse graph algorithms. Then we have this arsenal about all programming abstractions. Then for example, we want to implement the sparse diastrous shortest distance algorithm. Then we can pick oblivious data structure that is oblivious heap. And then you pick a loop coalescing abstraction to implement them. Okay, then using these tools, we actually implement three different sparse graph algorithms, and everything looks fine, right? But we have a very unexpected result. Is that our implemented algorithm made a theoretical breakthrough. So for example, all these three algorithms have better asymptotic complexity than the state of the art. So this is very surprising to us. And for more detail about all those algorithms, I would also like to refer you to the reader. Okay, so how do we actually do that? So I will, as I just promised several minutes ago, that I will introduce you one program abstraction that is loop coalescing. So this is a deep detail. So in secure computation, it is very challenging to implement a secret loop in the context. In secure computation, because the loop itself will leak, the number of iterations of the loop will leak information. So here we allow to write to the programmers to write a bounded loop. For example, we allow the loop to have a secret guard, but we ask the programmer to provide the public bound of the loop. So this is a nested loop, and the interesting thing is that in the inner loop from line 4 to line 7, so the bound M is not the bound for the bound for each iteration of the outer loop, but that is a total bound for the entire execution of the two nested loop, so that we don't do repeating things. So for example, if we provide a bound, a natural way is to make n times m iterations, but here we only make n plus m iterations. And then our compiler will analyze this code and then automatically transform that into the following one, that it looks like a state machine, so that we do not incur any extra complexity of the algorithm. And so with all these techniques, so what can we achieve? So I have mentioned that for the matrix factorization, it spent about more than 1.5 research a year. So what can we do now using ObliVM? So that is very surprising. We only do that in 1 day. Only one PhD student can implement everything in 1 day. So you may wonder whether it is efficient or not. For example, that might not be efficient. So, but the thing is that we can achieve 10 to 20 times faster. So that is even better. So this is what we can do today. So I believe ObliVM is a valuable thing for all secure computation developers. Okay, so let's look at the detailed breakdown of the performance gain. So we gave the result of the diastrous algorithm, and more results will be shown in the paper. So ObliVM although I focus on the programming language part of ObliVM, actually it has a highly optimized backend called ObliVM SC that is already open source. And you can visit our website for the link. And we implement the state-of-the-art circuit ORM that is optimized for secure computation. And this single thing, we compare our system with the best previous solution published in CCS 2012. So the circuit ORM itself can gain us about 50 times performance speedup. And the language and compiler can give us about 2,500 speedup. And further, we also did some other backend optimizations, and those details can be found in our paper. So that also gains us 7 times speedup. So in total, we achieve about 1 million times speedup. So that's a huge thing. So give you even more intuitive solution. So in 2012, in that same paper, they did binary search over 1 gigabyte of database, and only one single query spent about more than 12 hours to compute. And what about today? So using our ObliVM framework, it only requires 7.3 seconds for each query. Okay, we also compare our SCVM framework with an insecure solution. For example, the plain program running on top of x86 machine or something like that, and we compute the slowdown. So there is a very moderate slowdown. For example, for the distributed GWAS, so the slowdown is only 113. So 30. So we can expect that in the future this number will be even slower. Okay, so there are several collaborations with us that our ObliVM has been adopted in all these places, and we just won one task of the genomic analysis competition in March. That was 2 months ago, and we are for future directions. We are adapting our ObliVM framework to more cryptography tasks like fully homomorphic encryption and something more. So thank you very much. Here is my talk. I'd like to take questions.
Hi. So the example you gave right at the beginning of binary search, what would that look like? Like, what would the programmer have to write?
So which example are you referring to?
Like right at the beginning, you gave an example of binary search, and you said,
So this is the so the left part of this figure is what the programmer need to write for the loop coalescing. So you mentioned the binary search example, right?
Right.
Yeah, I think that's a good point. So the thing is that let me go back to there. Oh, okay, here. There you go. So this is actually what programmer need to, let me see if it can come up. Yeah, this program can be compiled in our ObliVM compiler.
So the compiler will handle the memory access by itself? Yeah. So
yes, the compiler can figure that out, which part need to be placed in ORM and which part do not need to do that.
Okay, so is it a potential use for ObliVM to have it just output like C code instead of a circuit so that you can take basically an arbitrary program and turn it into one that doesn't have side channels?
Oh, yeah, that's a very good question. So, yeah, it's a very interesting thing that our ObliVM compiler actually emits Java code. Okay. Yeah, and then the Java code, running the Java code will actually produce the circuit. So I think that's a very good question that. And I think that will be an interesting future direction to see how our ObliVM compiler can be customized to avoid side channels.
Okay, thanks.
Yeah, thank you. Huh? Actually, you can come to the microphone.
We don't have side channels. We don't have side channels. And this one, if you just write it like this, it will be compiled to generic ORAN, but you can alternatively just call our oblivious data structure. We have binary search trees implemented in our oblivious data structure. Those, if you use our oblivious data structure abstraction, it will cut a log n factor during the compilation. Okay. And it's very easy to emit a C code to just change the backend compiler. The more difficult part is in the front end. How do you compile to efficient circuits?
Thanks, Elaine.
Yeah, thank you, Elaine.
And I want to thank our speaker again.